Okay, this is the second video for section 6.4, and it's all about thermochemical equations. Here we have a diagram that is showing us the melting of 1 mole of water. So we've got solid water here, we've got liquid water here, and it shows us that the enthalpy increases as we go up. So recall, enthalpy, not a well-defined thermodynamic entity, but we know that the change in the enthalpy is important because we know that the heat of a reaction measured at constant pressure and the enthalpy are basically the same thing. We can measure the change in the enthalpy, and therefore we know how much heat is released in the process if the process is taking place at constant pressure. So the question that we ask is the delta H of this reaction positive or negative? Well, heat is absorbed by the system from the surroundings, and we can see that because the enthalpy starts out lower in the reactants and goes up and becomes higher in the products. Therefore, we see that the system is absorbing heat, and that means the process is endothermic. So if it's endothermic, the delta H is greater than 0, so therefore it has to be a positive value, a positive delta H. What it's telling us is that 6.01 kilojoules of energy are absorbed for every 1 mole of ice that melts at 0 degrees Celsius in 1 atmosphere of pressure. We can demonstrate that or show that by writing what's known as a thermochemical equation, which basically is the balanced chemical equation with the delta H written next to it. And it's basically saying that for every 1 mole of solid water that melts under these conditions of temperature and pressure, this is the amount of energy that's being released. 6.01 kilojoules per energy, or 6.01 kilojoules of energy is released for every 1 mole of water that melts. Here is a chemical process in which methane is reacting with oxygen to form carbon dioxide and water. And again, we see that the enthalpy increases as we go up. And so here are our reactants, here are our products, and the reactants have a greater amount of enthalpy than the product. So we ask, is the delta H negative or positive? Well, that can be pretty much seen right there that it's negative. Because the enthalpy is decreasing, the heat must be given off by the system to the surroundings. So is the delta H negative or positive? Well, the system gives off heat. Therefore, the process is exothermic, and the delta H is less than 0. So, in a written statement, 890.4 kilojoules of energy are released for every 1 mole of methane that is combusted at 25 degrees Celsius in 1 atmosphere of pressure. So we can rewrite that statement, only we can do it in a shorthand method, the thermochemical equation, which shows us the balanced chemical equation plus the delta H of the process. And of course, it is saying exactly what these words are saying here, that for every 1 mole of CH4 that reacts, 890.4 kilojoules of energy are released. And this is also true for every 2 moles of oxygen that react. So for every 1 mole of oxygen, we get this much energy released. For every 2 moles of oxygen, we get this much energy released. For every 1 mole of carbon dioxide formed, we get this much energy released. And for every 2 moles of water that are formed, this is the amount of energy that's released. The stoichiometric coefficients always refer to the number of moles of a substance, which is pretty obvious and is pretty much something that you saw in the past for chemical reactions in general. If you reverse a reaction, the sign of the delta H changes. So here's that process that we showed you before in which solid water was melting to liquid water, and for 1 mole of solid water that melts to liquid water at 0 degrees Celsius and 1 atmosphere of pressure, 6.01 kilojoules of energy is released. If we take it and change the sign, if we take it and reverse the reaction, and now the liquid water, which used to be a product here, is now a reactant, and the solid water, which is a reactant, is now a product, we see that when the delta H is rewritten for this new process, the reverse of the former process, we see that the sign gets changed. If you multiply both sides of the equation by a factor of n, then delta H must be changed by the same factor of n. So you see, we take this equation right up above, we're going to multiply both sides by 2, and when we do, 12.0 kilojoules of energy is released for every 2 moles of H2O that reacts. The physical states of all reactants and products must be specified in thermochemical equations. So you see, we have solid water becoming liquid water at an expense of 6.01 kilojoules of energy. Same equation now, looks pretty much the same, but the difference is that liquid water is now becoming gaseous water. And we can see that the delta H is different. So the delta H as water is vaporized to a gas is much higher than when solid water melts and becomes a liquid. Here's an example. How much heat is evolved when 266 grams of white phosphorus, P4, burn in air? Well, first we need the balanced chemical equation with the delta H, therefore making it the thermochemical equation. And remember, it says that for every 1 mole of P4 that burns, 3,013 kilojoules of energy are being released. But this is also true in terms of the fact that for every 5 moles of O2 that reacts, this much energy is released, and for every 1 mole of P4O10 that is produced, this is the amount of energy that's released. So if we've got 266 grams of white phosphorus, we want to know how much energy is released. We take the number of grams of the white phosphorus and we convert it to moles by dividing it by its molar mass, obviously. So that'll be the number of moles. Now remember, this is telling us that 3,013 kilojoules of energy is released for every 1 mole of P4 that burns. We don't have 1 mole, we've got 266 divided by 123.9 moles worth of P4. So we're now going to multiply that times the number of kilojoules per 1 mole. And of course, if we multiply these things out, cross out the grams, moles cancel with moles, we find out that 6,470 kilojoules of energy is released when 1 mole of P4 burns. We get 3,013 kilojoules released, and when 266 grams, which is a little more than 2 moles, we get 6,470 kilojoules of energy being released. Now, if this were, say, 266 grams of oxygen, this obviously would be the molar mass of oxygen here instead. Would this be a 1? The answer is no. Because remember, this is the amount of energy that's released per 1 mole of P4, but it's the amount of energy that's released when 5 moles of O2 react. So if this were 266 grams of O2 instead, as we said, this would be 32 grams of oxygen to convert the number of grams of oxygen to moles, but we would multiply it times the delta H per 5 moles of O2, and we'd get a different value. Okay, well that's that equation, or I'm sorry, not equation, that's that video for now, and I hope you find this exciting and fascinating. And if you have any questions, you can see me or Mr. Walsh tomorrow. So we'll see you then. Bye.